Okay, so question 9, the final part here of homework 7-3. Question 9 is the only one we have to wrap up, so I'll try to make this fairly brief. And I'll go ahead and write my answer first if you guys want to check that and just be done. But I got the moment of inertia was alpha times L to the fourth over 4. Right, so anyway, if you need to see where that comes from, then obviously I will work that out here. So suppose a rod is non-uniform such that its mass per length varies linearly with x according to the following expression, where alpha, I should say, is a constant. Find the moment of inertia of the rod pivoted about one end. So again, just like we did for question 8, as always, we start with the moment of inertia, which would be the integral from our parameters. So in this case, if I'm pivoting the rod about one end, if I'm defining that as 0, then I'm defining the other end probably as, right, L, as the length of the rod. So from 0 to L, right, and then it's always r squared dm, where dm once again represents the mass per strip. Right, so we've actually seen a question like this before when we did the center of mass. We hadn't yet done one with the moment of inertia, so I figured I'd throw this at you too, although hopefully you guys agree that it's not really much worse than what we did for the center of mass. But again, the key as always is finding dm. Right, so dm, what does that represent? Well, that represents the mass per little strip, right? So we're taking an infinite number of those little strips, and we're going to find the mass per strip of that process, right? So as I look at this, again, dm, the mass per strip, how would I calculate the amount of mass per strip? Well, I need to know, normally we would do like the mass per length because that would be the linear density, but they're saying it's not uniform, so I'm not going to use that. So instead, I'm going to use this linear density, this row that they've defined for me here of alpha and x. Right, so excuse me, not a row, that's a lambda, but sorry, my Greek letters are a little rusty. But anyway, lambda equals alpha x. So this is representing the mass per length. So then all I really have to do is take this, if you will, this linear density, if you will, and multiply that by the length of each of those strips. Well, what would the length of each of those strips be? Well, probably we'd call it dx, right? Or dr, depending on what you want to use, but I'll probably refer to that as dx. So my dm then would be, again, alpha times x. It'd be my lambda, my mass per length, times the change in length, so the change in dx. Right, so this is my function. So then that's what I'm going to plug in for dm. So the only thing that I am going to change here to make this consistent, right, since I'm referring to the change in length as dx, I'm going to make my r and x just to keep that consistent with my dx, right? R is representing that length, that position. So from 0 to L for x squared, and then alpha x, again calling this dx, and then all I have to do at this point is clean it up and calculate, right? Since alpha is a constant, I can go ahead and pull that out front of the integral, right? So my moment of inertia equals alpha times the integral of that. Now looks a little bit like a fish because of that dot there, but the integral of 0 to L, and then x squared times another x, so x to the third, and then dx. So again, when we integrate this, hopefully at this point in the year we're getting pretty comfortable with that. But my moment of inertia would be alpha times the integral of this, so 1/4 x to the fourth. And since I'm going from 0 to L, I plug in both 0, which would cancel that out, and I plug in L, which would obviously then make this alpha times L to the fourth over 4. Right? So I substitute L and I just move it to the top of the fraction, and that's where I got my final answer of alpha times L to the 4 over 4. So anyway, this is the type of question that we do want to make sure we're getting pretty comfortable with. I would expect you to be comfortable whether it is a one-dimensional rod or a two-dimensional disc. And even really a three-dimensional cylinder, as we saw in class, would be something that I would hope we could tackle as well if need be. But anyway, if you do have questions on this stuff, I know this is obviously the new part with the calculus and probably one of the tougher parts of this chapter. So if you do have any questions on this, let me know and let me get you some extra practice. But hopefully after you've done these types of questions a few times, you guys will agree that it's not a terrible process as long as we can identify what that change in mass is. But anyway, that finishes out then homework 3. And so just make sure, again, if you have any questions before the quiz on this stuff, let me know and be proactive about it.